You're placed into conference in muted mode.
To provide opportunities for networking, partnerships, and collaborations from across Canada and around the world. We provide support to translate research to commercial success. C supports Canada's National Design Network. National Design Network is formed by 52 universities and colleges across Canada. It has 1,500 faculty and research staff, 3,000 postgraduate students, and 500 connected companies. In the past 5 years, 8,000 researchers in Canada's National Design Network benefited from industry tools, technologies, and services valued at over $100 million. More than 100 Canadian companies have collaborated with academic researchers or hired grad students with microsystem competence and experience. CMC about making things. From to manufacturing, have capabilities and skills through our partners from photonics, microelectronics, MEMS, microfluidics, and embedded systems. In addition to offer these technologies through leading Canadian and international commercial suppliers such as Micralyne, we also offer in parallel to access Canadian government, non-profit, and university fab facilities, lowering the research cost from supporting you directly with NSERC dollars to accommodating the demand and leveraging national design network scope to lower the overall cost. We have about 30 engineers across different domains to support your research. Here, CMC MEMS MPW Service portfolio. At hand side as the MPW service managed by CMC. First, we offer the Micralyne MicraGEM-Si technology, which will be presented in this webinar. Also offer the Talendon MIDIS process, which is a very good process for initial sensor development. We offer UW MEMS through Surface at University of Waterloo. This is a gold-based process for RF applications. Besides those MPW services, we are brokering MEMS technology. It includes the newly introduced piezo MEMS process for piezoelectric-based sensors, general purpose poly-MEMS, as well as the iso MEMS technology, and the nickel-based metal MEMS technology. I'll pass the presentation to Dean to introduce the MicraGEM-Si technology.
All right. My name is Dean Spicer. I'm a process development manager at Micralyne, and today I want to share with you, basically give you a walkthrough of the platform we've developed. I call it the MicraGEM-Si platform. Quick of where we're going today. I'm going to give you really one slide about Micralyne, just give you some familiarity with our company if you haven't heard of us already, and then a brief introduction and key enabling technologies. I'll spend a little bit of time talking about what we needed beforehand before we could actually put this platform together. I'm going to spend a considerable amount of time walking through the process platform itself, kind of through the major steps of the process. One example of a device that we built on the inaugural run, just to give designers an idea of what is possible, and a summary slide. Micralyne. We are an independent MEMS foundry, and one of the world's independent foundries. We're not a captive fab in any way. We're located up in Edmonton, Alberta, Canada. We've been around since 1982, first as a spin-off of the University of Alberta, and at the time we were under the name AMC, or Alberta Microelectronics Center. In 1998, we were commercialized as a private company under the name Micralyne. Since our inception, we have worked with over 350 companies, ranging from Fortune 500 companies to innovative startups. We're most renowned for being able to creatively solve R&D problems, and are known for our ability to be very creative and solve some technically challenging problems in application space. We have a state-of-the-art MEMS facility up in Edmonton, Alberta, Canada. It's about 50,000 square feet. We handle 6-inch wafers, but we do have legacy 4-inch line as well. We compile with ISO 9001 as well as ISO 1345, which is the ISO for medical devices. I think we are one of the only, if not a few, if not only medical devices certified ISO company in the MEMS field. Okay, MicraGEM-Si. This is a process we're offering to academic and industrial users, and is particularly geared for micro MEMS or micro optical MEMS, optical switches, resonators, inertial, and biosensors. In collaboration with CMC, is a big part of helping us refine the process and developing a design kit and design rule checker for it. Some of the big things that kind of make this technology work. See a cartoon on the bottom right there of the old generalized cross-section structure, but basically there are SOI wafers that are bonded together, two SOI device layers to structure with bulk wafer machining. We use etching on the upper and lower device layers, and are aligned with sufficient accuracy to enable vertical comb drive structures. I believe this is one of the differentiators of this technology from others, is its ability to make manufacturable comb drives. Bond is also electrically connecting, so that you can route signals off from the top device layer to the bottom device layer and connect up electrodes or what have you on the bottom. Low stress gold metallization is also available on the top surface, suited for making bond pads, as well as highly reflective surfaces needed for things like optical mirrors. Enabling technologies I've already discussed a little here, but the deep etching of the base wafer in particular, some of the aspects that make that work is that it's a multi-level etch. So it's basically a nested etch that leaves 3 layers of functional silicon on the base wafer. And on the top right, you can see an image there of different heights available. These dark trenches are etched all the way to the buried oxide, and there's this level unique as well as that level, and then up here is the bonded surface. A key part of this, in one of the more difficult aspects, is keeping the surface bondable as we do this etching. One feature of this technology that makes it useful is our ability to do aligned fusion bonding. And on the right-hand side, you can see an acoustic image of a bonded wafer. We use to check our quality of our bonding and make sure everything is as we expect. Stepper lithography for this process. It is non-contact, which gives us a low defect count. Also unique to our kind of alignment scheme is its ability to align out-of-plane layers to within 0.4 microns. That's what enables our vertical comb drive capability. Low stress metallization needs to be mentioned. It's a ti-tungsten gold metal stack. And on the right-hand side here, I have basically a MEMS membrane, which is a mirror, with very flat surface, so it's not affected by the metal. The mirror is measured at the 1.5 radius of curvature, 1.55 meters, so it's essentially very flat. Comb drives deserves a mention even a little bit more than originally developed this process with this goal in mind, that we wanted to make manufacturable vertical comb drives. The reason we did is that vertical comb drives are more efficient than parallel plate actuators. The graph on the right illustrates a few of the differences between parallel plates and vertical comb. Plate kind of actuation is given by this orange curve. As you can see, it's very nonlinear and at the point where it kind of bends backwards onto itself, what will happen is the parallel plate will snap down, which is kind of desirable movement. The optical comb drive, by contrast, is much more linear in the region of operation, and actually it will never snap in the same way that a parallel plate will. What will happen is it'll actually go up like this, up the straight part, and it'll bend over and look kind of like an S. Basically, the fin's fully engaged. It can't actually snap down to anything. So it's desirable from that aspect as well. More efficient, you can get to higher and basically without as much driving voltage. Into the technology now, the process overview. In this slide is a generalized cross-section. Basically, the 3D image you saw previously, just kind of flattened out, so you can take a look at it in a little bit more detail. Also want to mention some characteristics of the silicon that we use for these application process. The upper two device layers are 0.01 to 0.02 ohm centimeters in their resistivity. The top layer is 30 microns, and the low device layer is 50 microns. Or the lower resistivity in this case is just to use those layers for conducting voltage. As contrast, the base wafer handle there's no doping added to that, so it's just mechanical. Base wafer thickness on the handle is 500 microns. Process steps. First step is to basically etch and define the kind of 3 levels in the base wafer. Step 2 is to pattern the backside of this wafer, so basically this section right in there. I'll go into more detail into that in the next slide. At this point, we'll bond the base wafer to the top wafer, the top SOI handle and the buried oxide, metal, top wafer, and pattern it. And pattern the release etch, and release basically singulates the devices and finish the process. Last step is singulation. We do use a wet saw, conventional wet saw for this. We actually use a dry laser process to singulate these die. About that in later. Step in a little more detail. Pattern etching of the base wafer. This is, of all the steps, probably the most complicated one, but it also gives us the most flexibility in the process. Find 3 layers, trench 1, trench 2, and trench 3, as we call them, or 3 regions. Trench 1 is the region is etched all the way in the buried oxide. 2 is basically etched 35 microns, plus or minus 2 microns. This leaves features that are about 15 microns sitting on the buried oxide, and you can see some of them over here on the right. I've annotated them. Our regions that are at 10 microns, plus or minus 1, leaving a micron silicon feature on the buried oxide, and I've pointed at one of them in the diagram. Regions that are not drawn in trench 1, trench 2, or trench 3 are considered the bonding surface, and I pointed out those as well. So the surface, obviously, if you want to connect upper device layer to lower device layer, maybe for a bond pad or for mechanical connection, you'd have to leave it out of the regions trench 1, trench 2, and trench 3. Some features in each of these regions are a little bit different. The biggest features, so for trench 1, minimum line and minimum space 4 microns. So in that region there. In trench 2, lines and spaces you can have there are 3 microns, and then in trench 3 you can have 1 micron lines and spaces. Step 2 is basically etching the partner wafer, what would become the top wafer. It's a fairly simple timed etch, 20 microns in depth. Some of the features in this case are 1.5 micron lines and 1.5 micron spaces. Keep in mind that the regions that are etched in this case in the final structure can become 10 micron membranes. 3 is to bond the two wafers we just created together, and the cartoon shows that, noting on interface there. The bond accuracy at this point is plus or minus 10 microns. Also of importance is that the bond is mechanical, but it's also an electrical connection between the two layers of silicon. If you want to route signal from the top down into, let's say, an electrode down here, you do it this way. Before, we remove the top SOI handle, and this is a grind and polish process. We basically grind and then stop short, followed by polish, and then stop on the buried oxide. At that point, the buried oxide is stripped, which leaves us with a pristine silicon surface that is optically flat and good for things like optical MEMS. At this point, we deposit the stress metal, and this is a blanket deposition. The residual metal stress is 40 to 140 megapascals. I've already mentioned that it is tungsten gold metallization. The metal is then patterned to device elements like electrodes, bond pads, or just leaving metal on the reflective surfaces that you desire. This is also, I should mention, the place to put things like lettering and annotations and labels and things like that. This is the layer that I recommend for that use. I recommend using the deep edges and things like that for that. It's better to put it into the metal layer. Finally, the release patterning and etching. The final process completely etches through the 30 micron thick top device layer and releases the MEMS structures. Keep in mind that during this process, the features in the lower layers can be exposed to some over etching. Basically, the higher aspect ratio features will expose the lower regions less to over etching, but wide open regions will basically expose the bottom layer to the most over etching. To give an magnitude to the over etching I'm talking about, is somewhere between 1 to 4 microns, depending on the aspect ratio kind of available to the etch gases. The other important thing about this release pattern is that it is within 0.4 microns of the device layer pattern, which enables us to do those vertical comb drives. Singulation, this is done, as I mentioned, by a dry process, which is a laser dicing. Basically, what it does is it focuses down inside the silicon, and then in the section kind of rasters back and forth, go upwards through the silicon, creating a scrub line, and it is basically inside the silicon. At that point, the shape on which the wafer is sitting is stretched, and all the singulate. This is a great process. It doesn't damage the parts in any way, and for the most part is particles and problems like that. An example of something that we did on the very first run is a VOA, a variable optical attenuator, an optical MEMS part. It uses vertical comb drives, as you can see up on this side of the mirror and also on that side of the mirror. The mirror itself is held at ground potential. This pad here. This top can be a voltage applied to it, and the voltage will track through here onto the piece of silicon that's sitting onto the lower combs, and then it'll act to engage the combs as you apply more potential. The performance device is shown on the right-hand side. As you can see, it moves, let's say, 0.4 degrees at about 5 volts. Note that the mirror is very flat, even with the tungsten gold metallization on top of it, and its radius of curvature is better than 1.5 meters. Highlights of this process. In summary, we present this process for academic and industrial users to make use of as a robust way to get devices into manufacturing or to prototype devices. One other note is that the basic processes illustrated here are also used by Micralyne in more complicated process flows. If ever your imagination takes you in a way that beyond the capability of MicraGEM-Si platform as described here, please just contact us directly for your manufacturing needs. Thank you. We're open for questions if anybody has some at this time.
Welcome for the introduction of this process. I will continue to talk a little bit more about the MPW service, and then we will open for questions. So the MicraGEM-Si technology is scheduled 3 rounds per year. The first fabrication run design submission done is set at June 4th, 2014. More information about the future rounds, you can check our fab schedule on our website. There are 3 standard dimensions for the process, 4 by 4 millimeter square, 4 by 8, and 8 by 8 millimeter square. If you need a larger area, please contact CMC. Pricing has 4 categories. For Canadian academic users, we have a prototyping subscription service. For subscribers, if your application goes through the peer review process and get granted, the price is $750 for a 4 by 4 millimeter square area. If you go through the peer review process, the academic price for subscribers is $3,500. For unsubscriber academic price, it's $4,800, and for industry users, the price is $6,000. The delivery quantity is 50 copies for each design. If you need more copies, please contact CMC before the run starts. We process design kit in 10 MEMS per edge right now. It provides the layout and DRC function. And you might have a converter function design tool soon. Some additional service available. For this process, we provide short-term CAD tool rental. You can rent the Tanner EDA tool for your layout, and you rent the ANSYS tool for assembly. After you get chips back, we also provide packaging and assembly service. And wire bond your die to standard packaging like PGA package, DIP type. We also provide standard test fixtures for those package types. Moreover, we also provide die bumping and flip chip services, die unstacking, and die on board. We have design consultation and engineer support for the process, so if you have any questions, feel free to contact CMC directly. We also provide test equipment rental, so you can use equipment to test your device. We have an online design rule checking server, so you submit your design to CMC and receive the DRC report automatically. Here's a description of how to get started. It's very simple. First, you can download the design kit from CMC website, and you need to reserve your design space through CMC. For Canadian academic users, please submit the RFMR application form online. And for industry and non-Canadian academic users, please contact Refilter directly. After reserve the design space, you just need to submit your design to CMC before the design submission deadline, and 3 months later you will get your device back. If you have technical questions, feel free to contact me at yng@cmc.ca. Then presentation. So now we are open for the questions. We got a question.
Conference has been unmuted.
Okay, so the first question is if it's possible to put gold layer on the bottom wafer. A quick is no, this cannot be put on the bottom wafer in the MPW service, but you can use the bottom silicon layer as electrodes for application. Dean, do you want to extend on this question?
Sure, I can maybe just elaborate in a way why that's not possible. We are essentially using a fusion bond process to bond the wafers together. And after that process, or as part of that process, there is an anneal at temperature, which would destroy any metals that are kind of on the bottom layer.
So any other questions?
Can you?
Yeah, speaking.
Oh, can you, is bonding in air or vacuum?
Answer that one. The bonding is actually done in a controlled environment inside a bonder under vacuum.
What's the vacuum level? Millimeter?
Good question. It's a rough vacuum, not under high level vacuum. So
yeah.
10⁻³ to the 4.
Second question is the bottom device layer has 3 possible patterning steps. Are they fixed heights?
For this form, yes, they're at fixed heights. If you require some, variation on that, obviously we can accommodate, but it wouldn't be part of the MPW process. Everybody has to share the same steps for the MPW.
And what are the heights?
That was shown. Let me just go back to my PowerPoint here. For the base wafer etch. Yeah. So the trench 1 region is all the way to the bird side, which is a 50 micron etch. So the base device layer is 50 microns. The second etch is 35 microns down with 15 micron silicon. The other etch is a 10 micron etch, so it leaves a 40 micron silicon feature.
Okay, so 35 microns down from the top of the device layer is trench 2?
Yes.
And then the last one is 10 microns down from the top?
Yes, exactly.
Okay.
So I just want to extend this question. Your purpose to check the vacuum condition is, are you trying to create a vacuum chambers based in the process?
Yeah. Can you create a sealed membrane?
We can. We haven't actually published the vacuum level, but that's something we should consider including in the design kit, I think.
Right. Okay. And there's no dielectric insulation layer between the gaps.
Which
what will be your top electrodes and what would be your bottom electrodes? There's no dielectric there?
No, there's not. And after the bond anneal, those silicon structure basically electrically connected.
Right.
The bonding itself is silicon to silicon. It's a direct bond.
Right. Doing a top and bottom electrode, you'd have to dump device, and it would be separate from the bottom patterning.
Well, what you can do is create cutouts, and so that it cuts out a region of silicon that is isolated in the top device layer and the bottom, except maybe a line that goes to an electrode underneath, and then you have a separate region in the layer that is your other electrode. You basically have to just cut them out. Does that make sense?
Yeah.
I don't know if you can see my desktop at this time. Maybe not. Krista, could you share my desktop at the moment?
Yep.
Or allow me to do that. Can you do that now? So yeah, you can see in cartoon that kind of idea illustrated where there's this surface here, the bond surface would be connected to something on the top and cut out, and but is also connected to this, basically a silicon structure that is an electrode over here. And if you look at, look to my VOA example. If you look at this, you can see like this bond pad at the top here is cut out. It is basically isolated from the surrounding region of the die. So this region of the die is held at this one here can be powered, which puts power to the lower combs and actually actuates this device.
That cutout would go all the way through to the bottom box layer.
That's right.
Okay.
If you're trying to create a sealed cavity and have electrodes feeding into there, I don't believe that's possible. There'd always be like cutout.
Right. Top and bottom would always be at the same potential.
Right. If you're creating a sealed cavity. Yeah.
Right.
Okay. So, is there any other question?
Thank.
Yeah, speaking.
There's one question regarding the thickness of trench 1, 2, and 3. Is it fixed thickness, or we can, for example, thickness of 30 micrometers, 25 micrometers, etc.
You mean that's customize the thickness of the trench etching?
Yeah.
So process recipe is fixed by now, but if you have any thickness requirement other than the fixed recipe, please let us know. We may try to consider it.
Okay. Okay. So then in all the design we have to have the same thickness.
Question? Well, I thank you everyone for attending this webinar. Just for your information, the webinar is recorded and it will be online in the next couple of weeks. Thank you again everyone for attending this presentation, and thank you, Dean, for providing insight of the technology. This webinar will end here, and wish you have a good day. Thank you. Bye.
Thank you.